and then the Earth cooled off. And this gradual erratic cooling is due to plate tectonics. And at this point, I think Antarctica separated, the Drake Passage opened from South America and so forth. Various things happened. I've blown up the last 3 million years because from that point on, there were some dramatic climate changes. And these are the current ice ages. And the strange thing is, so during this time, the continents didn't drift very much. The continents were essentially the same position here as over there. This is due to changes in sunlight. These are the recurrent ice ages. And I would argue that this plot is the most important one, persuading you that global warming is a problem. That we happen to be today at a very precarious moment. We're right there where the red star is. And we get this data by drilling into the seafloor. We can blow up this last bit by drilling into ice cores in Antarctica. We get that plot for carbon dioxide and temperature. And you notice that in this last little bit at the very end, the last 10,000 years, right there, we humans have taken advantage of favorable conditions. So the ice ages are separated by relatively brief interglacials, when climatic conditions are far more favorable for us than at other times. And during that time, the most recent one, we've accomplished just about everything we're proud of. We invented agriculture, we built cities, civilizations. Everything we've accomplished was in that little span of time, was at this point. And we developed so rapidly that we're increasing CO2 as the red spike at the end. And if you Al Gore, then you look at that top graph, the two plots, and you see that whenever carbon dioxide goes up, the temperature goes up. Whenever carbon dioxide goes down, the temperature goes down. Oh no. What happens? This one?
Yeah.
Okay. So from this plot, you suggest we're going to face global warming invariably, right? Every time CO2 went down, temperature went down. When CO2 went up, temperature went up. There's a serious flaw with this argument, and we can quiz the students, but correlations do not imply causality. And you shouldn't infer simply because you have these correlations. They could both be caused by something else. And it so happens actually our cause. The ice ages have external cause. And we still haven't explained very well what is going on here. What is intriguing, if you blow up any other part of this record, you do not see this. So we live in a most unusual time, and because of our activities, this is a most precarious moment in the future of the planet, in the sense that take away our activities, and from this record you would predict that the next ice age is imminent. We could be stopping it, but we're doing it in a great rush. The time scale here is millennia. We're doing it in a decade or a few decades. And so what I want to emphasize, there is lots of uncertainty, and I'm astonished by people. Everybody now seems convinced global warming has started. We're playing with fire. Right? We don't know what we're doing. Because we can't explain, we don't really have very convincing explanations for the ice ages and so forth. We can come back to this. But we should be circumspect, we should be cautious. And above all, we should turn almost to the ethical questions. Given all this information, how should we now respond? But before we do that, let me just point out a few implications of this record, that what characterizes Earth's climate is change, constant change. And it means the picture you see here, a spectacular picture of I'm trying to move to the next one. A spectacular picture of planet Earth taken from space. And we're all familiar with the deserts and jungles. And it may come as a surprise not to this room, you're all oceanographers, but the oceans have as much diversity in climatic zones and in life forms as do the continents. And if you want to understand this picture, you have to know something about the atmospheric circulation. You also have to know even more about the oceanic circulation. The thing to keep in mind is that this is just one snapshot from a panorama that's constantly changing. And the constant changes would be those ones. So there's continual change. And in fact, I can show you, we have all sorts of instruments to monitor what's going on today. And this is the Toga Array in the tropical Pacific, mostly there to monitor El Nino. Notice that some of the instruments are satellite. They're listed down here. There are tide gauges, drifting buoys. And the satellite tell us quite a bit about the changes. And so I want to impress on you that we have these continuous changes. So at this point,
video?
Yeah.
Ian, can you come here for a second?
As that's not really essential, I can.
Well, it's there. I just have to make sure the video is on the desktop. Not this video, the video, that's one.
And what you're mostly seeing is the seasonal cycle. But I want to try and impress on you how things change on a huge, broad spectrum of frequencies. So these are mostly the seasonal changes. And they're not obvious at all if in response to the Harvard people, if supposedly the right answer is the Earth's axis tilts, then you should see this north-south progression. But in reality, look what happens along the equator. Things seem to move east-west much more. So there are fascinating problems in the seasonal cycle that we don't understand. That brings us back to the Harvard one. That's enough. So the longer-term changes, we don't have measurements. No. We don't have measurements, but this one. Okay. And you can wonder, how do we know about things such as ice ages? And it's major effort. So I already mentioned you need to know something about the oceans, the atmosphere. You need to know something about glaciers. You find in weird places, you find the rocks, such as these. How on earth do they get there? And they're given the name errant rocks. And it's our glacier, so some giant must have moved it here. And the giant turns out to be a glacier. And the glacier, conveniently, after it's done its thing, can disappear. There's no trace of a glacier. And it simply requires temperatures to go up and down, which gave Milankovitch the idea that the ice ages were really due to changes in orbital parameters that cause temperatures to rise and fall, and that translates into this. So there's a rich body of information, the next one, that the conclusion we come to in the end, that Earth is habitable because it's a recycling planet. And if I were to seal off the room completely so no fresh air comes in or out, then we will be in considerable discomfort very soon, because we inhale oxygen but we exhale carbon dioxide. And if we insist on sealing off the room, we'll all be dead in due course. We can avoid that by bringing in plants into the room. The plants will do photosynthesis, and that gives us the benefit. They will convert CO2 back into oxygen, provided they have a source of energy, sunlight, and provided they have a source of water. And so now the picture becomes more complicated. You have to recirculate not only oxygen and CO2, you also have to recirculate water. And very quickly you find that, and you have to maintain that over 4 billion years, and that's where the land comes in. So we have a planet that operates in this manner. It gets sunlight from the sun, and it sends back infrared light, and it uses that energy plus energy internal to the Earth to stay in constant motion. So the main feature, we have a planet that is constantly changing. What we see today is just one snapshot of many possibilities. That snapshot changes day to day, season to season, decade to decade, over the millennia. If I sound a bit skeptical, as I said earlier, that I question our certainty that global warming has started. And this gets probably some people upset. My reason is simply that 1,000 years ago, Greenland was far more habitable than it is today. Greenland had a population. We know for a fact that CO2 was no different 1,000 years ago from today. So the variability has a forced component, external factors such as changes in sunlight, forces changes. In addition, it has spontaneous variability about which we know very little. We know a lot about spontaneous variability day to day, that's weather, and we can even predict it now. We can't predict why next summer is going to be all that different from this summer. Even sunlight is going to be the same. And when you get to decades and longer time scales, we know even less. And so it's not clear to me we should be so certain that what we see is evidence for human activities. The IPCC is very honest about this, and in their reports state that the increase in temperature over the last 100 years is very tiny. It's something like 1 or 2 degrees centigrade. About 50% is probably due to humans, and the other 50% is just spontaneous. We cannot explain it. So I just want to emphasize there is uncertainty. What I want to go back quickly to my complaint about the Harvard video, that it gives the impression science is a collection of facts. So suppose you had to conduct interview with Harvard students and you ask them why is summer warmer than winter. A far more interesting response than one is the following, instead of the one you saw in the video. If the Harvard students tell you that summer is warmer than winter because the Earth is closer to the sun in summer than in winter, then that implies that its orbit must be an ellipse. So you could then go and make astronomical measurements, and you find indeed the orbit is an ellipse, and we are closest to the sun on the 3rd of January. That's perihelion. Okay, so the Harvard students aren't dummies. They'll realize that 3rd of January is actually winter in Cambridge, Massachusetts. It's not summer. So there must be more to the story. So they can call their friends in Cape Town or Melbourne or wherever and find out that it actually is summer in the southern hemisphere. And so they'll come up with a new hypothesis. And the new hypothesis is the Earth's axis tilts. And this introduced entirely different dates associated with the solstice. So even if the Earth's orbit were a circle and we were exactly the same distance from the sun all the time, we would still have seasons, because at certain times the axis would point towards the sun and at other times away. Okay, so now we have two. In reality, there are two reasons for the seasons. The one is the tilt, the other one is the eccentricity of the orbit. Each is associated with a tip, with a tilt. Each is associated with seasonal cycle. So now, how do I deal? So the Harvard people are only half right, and half wrong. So the story becomes even more interesting. If I play around with the top, how do I proceed? And my suggestion is play with the top. And you can't see if I spin a top here. But if a top spins, or if I can take a coin and spin it, as long as the axis of rotation is vertical, it's perfectly stable. It's the end of the story. But the moment the axis tilts, it precesses the top. The tilt itself will go through a circle. And the period for that circle is about 20,000 years. So what it does is change those dates, 3rd of January 22. They're constantly changing because the tilt, when you point towards the sun, when you are closest to the sun, those dates change relative to one another. There are occasions on which they coincide. So today, the southern hemisphere has more intense summers than does the northern hemisphere, because those two line up, right? The southern solstice and the perihelion. 10,000 years ago was the opposite. So if we go back 10,000 years ago, perihelion was in June. Northern summer solstice was in June. So what will exceptionally intense sunlight in summer do for you, especially in the tropics? It will cause India to have exceptionally intense monsoons. The monsoons is what mostly brings rains in the tropics. It brings rains to Africa, West Africa, but only as far north as about 500 north of West Africa's coastline. Right? So most of the Sahara is a desert. However, if it's very intense, the monsoons will extend into the Sahara. So today the Sahara looks like this, and 10,000 years ago it looked like the next one. And if you question this, we can go to the next picture. I can take you to a trip to the Sahara, and you see those peculiar rock paintings. If you look close up, these were the animals that were in the Sahara, in that environment 10,000 years ago. Now, the story can't end there because this precession doesn't stop. It wasn't just 10,000 years ago. It must have happened repeatedly. What happens to the fresh water on the Sahara? It flows into the Mediterranean, a very salty sea. The fresh water on top of the Mediterranean stabilizes it, makes it anoxic. And the next picture, you get islands such as this. And so the black layers are created when the Sahara had lakes, and the white layers is today. And even the baby rocks know about this. So the main point here is that the story of the Harvard, the main story of the Harvard video is that it could be made a lot more fascinating. It can show people that by constantly questioning, any hypothesis you have should be tested. When the students tell you the Earth is closer to the sun in summer, don't dismiss them as stupid. Have them test the hypothesis, and it leads in unexpected directions. You can gain a lot. Just quickly, so I'm arguing that organized skepticism brings lots of benefits. And another benefit is progress is a hallmark of science. We constantly we may not know the answers to certain problems today, but we will in due course. And we've made enormous progress in global warming. The alarm was first sounded in the late 1800s by chemist Arrhenius, who hypothesized that because of the Industrial Revolution, the increase in atmospheric CO2 will lead to global warming. And he was a Swedish chemist. Sweden is rather an awful place in winter. And Arrhenius was very optimistic. He says Sweden will become a better place in winter. And he didn't live long enough to see that. But anyway, nobody paid attention to Arrhenius, arguing that CO2 will not accumulate in the atmosphere, that the ocean absorbs a lot of CO2, and that will keep things under control. It then took Keeling at Scripps in San Diego a few decades to develop an instrument to measure CO2, atmospheric CO2 levels extremely low. He measured it over the course of, he got measurements in, I think, late 50s, and quickly established that CO2 is indeed increasing. So we made progress. We know that CO2 is increasing. We know it's a greenhouse gas. And the next question is the temperature in the atmosphere. It's supposed to increase globally average temperature. So the first thing is to get some estimate and that took a while. We have very little data, it's sparse. It wasn't really until about 10, 15 years ago, a fellow at Berkeley, I forgot his name, Moeller, was actually funded by one of the Koch brothers to show there's no such thing as global warming. He was a physicist, and he used fancy statistical methods and established there is global warming. So temperature is increasing. So everybody agrees temperature is increasing somewhat erratically. The next question is, so it is increasing, how do you know the cause of it is CO2? And again, this is sort of where we are today. Part of it is CO2. I said the IPCC report is about half the increase is CO2. There are fingerprints, such as if it is greenhouse effect, then the stratosphere should be getting colder. It's a bit like insulating your attic. If you insulate your attic, then your house will get warmer, but your attic will get colder. And so in some sense, the stratosphere is our attic, and it is indeed getting colder. So there are various ways in convincing us that yes, CO2 is contributing to the increase in temperature. As I said, how much is still unknown. But my main point is what I made earlier. We're unsure about what will happen next. And the present, we can conclude, the present is this precarious moment, and it calls for caution and for tentativeness, circumspection. The main result from this organized skepticism is that there is no final result for any scientific question. All scientific results are tentative. All the scientific results are uncertain. Some people find this very upsetting. They like certainties. It's just a fact of life. You have to learn to live with uncertainties. You have to make decisions. Businessmen do it all the time. So I don't understand why they're so upset when they have to make decisions here, given uncertainties. But it's just science does not give final answers. We may think that Newton settled all issues until Einstein came along. And Einstein came along because they constantly tested Newton's laws. And there were some discrepancies. Forgotten Mercury's precession. There were various things that indicated Newton was not the end of the story. Similarly, so it's just a fact of life. Scientific results are tentative. So where we are at the moment, we have two approaches. We have a reductionist approach and we have a holistic approach. In the climate business, we married these two as regards weather prediction. So weather prediction up to World War II was a holistic exercise. You collect lots and lots of data, put it on a map, and you'll identify features, a low, a high, a warm front, a cold front. Looking at a series of maps, you can make a prediction. Okay, that was weather prediction up to World War II. Then somebody invented a computer, and you could adopt a reductionist approach. And the reductionist approach had equations. Initially, the computers, this was in the 1950s, they were so weak that the equations had to be simplified enormously, which raised interesting scientific questions. What is the simplest set of equations, the simplest world in which you can have weather? And it led to things like baroclinic instability, to Lorenz's chaos theory, and so forth. It was a very exciting time in meteorology in the 1950s. For the first time, we knew actually why is there weather. It turns out rotation and it equated to pole temperature gradient. It's a reductionist question. It took 30 years to marry those two approaches. And it wasn't until the 1980s that we use the computers, having trained them on all the available data, to predict the weather in the future. And the models that have used data to become good are so good they can tell you when the data is